Ako yung nag-wonder.
Dear students, please listen to sir, and now he is going to deliver lecture on cosmology. Yeah. So welcome, sir. Sir, please.
Those in the last row, can you hear me without a mic?
Sir,
आवाज आ रही है कि नहीं आ रही है? हाँ, आ रही है आवाज? Okay. How many people are comfortable in English? अंग्रेजी में comfortable कितने लोग हैं? अच्छा कितने लोग नहीं हैं?
कितने लोग नहीं हैं? बात करो उसमें क्या है?
ठीक है. Okay. हम इंग्लिश हिंदी मिक्स में बात करेंगे. पर अगर कहीं पे प्रॉब्लम हो तो मुझे रोक देना वहीं पे. ठीक है? ये सब बात समझनी है. बात समझ नहीं आएगी. साथ साथ ये भी है कि जैसे डार्क मैटर को हिंदी में पारिभाषिक हिंदी में कहते हैं सांद्र पदार्थ. दूरी रखे तो अच्छा है. ओके. सो एरिया मतलब मेरा जो मेन एरिया है वो फिजिक्स. फिजिक्स में ब्रांच कॉस्मोलॉजी. कॉस्मोलॉजी में एक टॉपिक है डार्क मैटर. हाउ मेनी ऑफ यू हैव हर्ड अबाउट डार्क मैटर? रेड अबाउट डार्क मैटर? न्यूज़पेपर आर्टिकल? नेट? गुड. मुझे डर था कि बहुत लोग पढ़ के आएंगे इसको, ये टॉपिक फिर बेकार हो. पर ठीक है, कम लोगों के बारे में जानकारी है. दैट्स गुड. दैट मीन्स यूजफुल टॉपिक. सो क्या बातें करें? बेसिकली डार्क मैटर है क्या? दैट्स द फर्स्ट क्वेश्चन. ओके. कैसे पता चलता है कि डार्क मैटर नाम की कोई चीज है? हाउ डू वी नो दैट इट एग्जिस्ट्स? एंड इट एग्जिस्ट्स. Where is it found? Where are all the places where dark matter? Most important question is what is it made of? पदार्थ कौन सा है? या एक तरह का है या कई तरह के पदार्थ? Final topic of this talk will be connecting big things with small things. बहुत बड़ी चीजें और बहुत छोटी चीजों को एक साथ जोड़ना, जो इस टॉपिक की खासियत है. So let me just start. Just start with bright matter. इसकी वजह से दिक्कत तो नहीं हो रही है इसको देखने में? There's too much bright matter. Are you all comfortable? दिख रहा है?
Yes.
Okay. So the question is what is bright matter? क्या है bright matter? किसको बोलेंगे bright matter? हाँ, anybody? कहाँ देखेंगे bright matter? कहाँ ढूंढेंगे? It's interesting is we look at the sky, and actually, what is the universe? So, sky, we are looking at the universe. A cosmologist is studying the universe as a whole, and And we do it by looking at the sky. That's the only way we have. And it's everything. The sky has everything there. In fact, when we look at the sky at night, we see some bright stars which are visible to the naked eye. बाकी चीज़ें दिखती नहीं हमें, पर एक शेर है ना, सितारों से आगे जहाँ और भी हैं, वो हम वहाँ हमारी जो खोज है वो वहाँ तक पहुँच गई है. We're looking at those things beyond the stars, beyond the visible stars, nearby stars. Okay. So these stars emit light. An example, our sun. The sun emits light, and there are other things that emit light, like clouds. दिल्ली में तो गैस क्लाउड दिखते ही नहीं है, but बागपत वगैरह में there's some chance if you look at the night sky there may be not that much clear. Actually ये जो लाइट है ना, इसको कॉस्मोलॉजिस्ट कई बार परेशान हो जाते हैं कि लाइट बहुत है, मीनिंग for study of the sky we want outside light minimum. So city lights are a very bad thing for astronomy. So you can't make a good telescope in Delhi. Delhi में telescope setup नहीं करते हैं हम, क्योंकि कुछ पता ही नहीं city lights की वजह से. So you can see glowing clouds of gas, you can see other objects if you're lucky, like quasars, etc. These are bright. They emit light. Clear? Please stop here. Tell me. Clear है? Okay. अब कुछ चीजें हैं जो लाइट एमिट नहीं करती हैं. ओके. So examples are many. Our own Earth, it doesn't emit its own light. It doesn't have its own radiation. In fact, all planets are like this. They are dark in this sense. So how do we see them? Planets कैसे नजर आते हैं हमें? बुध, मंगल, शुक्र वगैरह.
When sun reflects.
They reflect the light, of the sun. So we see them by reflected light, but otherwise they are dark. On their own, they are dark. So dark matter की अगर परिभाषा ढूंढें तो सबसे आसान परिभाषा है anything that doesn't emit light is dark. Okay, that's our first starting. इसको हम थोड़ा भी modify करेंगे आगे, but that's our so that's what I've called some subtleties. So collectively, anything that doesn't emit light of its own, which has no light to emit, so that means planets, satellites, comets, etc. Has anybody seen a comet? देखा? You must just look out for the next chance. जब भी newspapers, when net पे आए किसी comet का approach ज़रूर देखना. एंड इफ़ यू आर इन अ डार्किश प्लेस, थोड़ा रूरल एरिया में अगर हो तो और अच्छा है, क्योंकि देखने का मौका मिलेगा. दिल्ली में बहुत सारे कमेंट्स आते हैं, दिखते नहीं हैं. सो बट यू सी देम बाय रिफ्लेक्टेड लाइट. नाउ दिस इज द मोर कॉम्प्लिकेटेड स्लाइड. क्वेश्चन इज व्हाई शुड वी वरी अबाउट दिस? मतलब if you look at the mass of the solar system, we know the masses of all the objects in the solar system. Sun, major planets, minor planets, comets, सब हमें पता है. So you add everything, planets, asteroids, comets, etc. It's not even 1% of the total mass. The sun is just dominating. Sun का mass इतना ज़्यादा है कि बाकी बिल्कुल नगण्य है. They are not, sorry, I won't use such words. ऐसे शब्द हम दूर ही रखेंगे. 0.14% of the total mass, roughly, is contributed by other objects. The sun is everything. That means there is most of the matter in the solar system although there is a lot of dark matter in the solar system in the sense that we defined it, it's very little in terms of total quantity. कुछ भी नहीं है, 0.14% है. So then why should we worry? इतनी चिंता क्या है? और उसको स्टडी क्यों करते हैं लोग? Okay, so the answer is this. The solar system is a very small thing. हमें लगता है कि सोलर सिस्टम बहुत बड़ा है, पर एक्चुअली बहुत छोटा है. यूनिवर्स के स्केल पे सोलर सिस्टम इज अ वेरी स्मॉल ऑब्जेक्ट. ओके, व्हाट्स द साइज ऑफ द सोलर सिस्टम? डज एनीबॉडी रिमेंबर द डिस्टेंस बिटवीन अर्थ एंड सन? कितना है? कितना? वो सब बोलो.
1.496 in 10 की power 11 meters.
Excellent. So, 10 to the power 11 meters है. That's the scale of the solar system. अगर kilometer, millions of kilometers. So, what is the time taken from light to go from sun to earth? 8 minutes. 8 minutes. सबको पता है ना? 8 minutes. So, you can say the size of the Earth's orbit is 8 light minutes. Light minute is the time taken by light, the distance. Sorry, light minute is the distance covered by light in 1 minute. So now we have to go from light minutes to light years, and hundreds of light years. So that's the distance scale we are now going to be looking at. So that's why the solar system is very small. There's a lot of dark matter out there. ये out there शब्द बड़ा मजेदार है. Astronomers, cosmologists often say out there. Out there मतलब वहाँ बाहर. बाहर मतलब क्या? So everything that is out in the sky is out there. So in general there is a lot of dark matter out there. We don't know exactly where, but somewhere. And that dark matter is a lot. Is not negligible. So, so how should we detect dark matter? So, as you have all said, that planets are visible to the naked eye by reflected sunlight. Has everybody seen? How many people have seen Jupiter at night? हाथ खड़े करना जरा. Nobody. You don't look at the sky. Okay, no, some of you, but very small number. I thought more people would have seen. Saturn तो देखा ही नहीं होगा किसी ने. If you have binoculars, just take a small pair of binoculars and look at Saturn. You'll be able to get some idea of the rings. साफ तो नहीं दिखेंगे rings, पर कुछ दिखेगा. Okay, so up to Saturn you can actually see with the naked eye. But beyond Saturn, Uranus and Neptune. पहले प्लूटो भी आता था, अब प्लूटो को तो हटा दिया हमने. It's there, it exists where it is, but we don't count it as a major planet. So प्लूटो की गिनती अब minor planets में होती है. तो Uranus और Neptune है, पर उन्हें नहीं दिखते हैं, because they are too far. So most objects in the sky, which are far, we are not going to be able to see with reflected light alone. दूर हैं. So the clue for detecting dark matter comes from the story of Neptune, detection of Neptune. So what happened was first Uranus was detected. First of the planets to be found using a telescope was Uranus. Saturn तक ऐसे दिखते हैं, है ना? खाली आंखों से. So you need telescopes were very useful because Galileo used telescopes to find many features of Jupiter and Saturn which couldn't be seen to the naked eye. But he didn't see Uranus. It needed more powerful telescopes, and it was later that Uranus was finally seen. When people looked at the orbit of Uranus, they found some irregularities. After all, Newton's law तो सबको पता है ना? You know Newton's law, ना? Newton's law of motion and gravitation. दोनों पता है. So we can compute all the orbits. So when you computed the orbit of Uranus, it didn't seem to follow the regular pattern. It was a bit irregular. थोड़ा इधर उधर जाना था. क्यों? So the guess was that there's a varying extra gravitational pull. There is something else that is attracting it. When it goes close to that, the deviation is more. ज़्यादा हिल जाता है वो, जब पास आता है तो, और उससे दूर चला जाता है तो कम हिलता है. So that suggested an undiscovered planet, and that planet Neptune. Here's a photo of Neptune. Neptune looks blue. You can't see it unfortunately with the naked eye, so this blue color you don't see. But with a suitable telescope you can see Neptune. As I said, it has to be a little better than the telescopes used by Galileo at that time. So they have to be a little better than Galileo's original telescope, but not too much better. These are you can still set up in your own school or college when you are in college. An observatory with a cheap telescope which can see Neptune. So Neptune gives us the clue that we have to detect dark matter. How do we find dark matter? We find that there is a gravitational effect of this object which we are not able to see, such as Neptune in this case. And gravitational effects will always be there. Why? Why are gravitational effects always there? Newton बहुत पहले. What did Newton teach us? Every body attached every other body. So gravitation is universal. So no matter what the kind of dark matter that you are looking at, it may be very different from a planet like Neptune. No matter what kind of dark matter you are looking at and what distance scale you are looking at, as I said, we are just now going to be talking about much bigger distance scales. We can find them through their gravitational effects, and the gravitational effects alone by essentially. अच्छा भूख लगे ना उसे 15 मिनट पहले मुझे बता देना. लग रही है क्या भूख? So
बात नहीं बेटा.
For some time we'll talk about objects called spiral galaxies. What are spiral galaxies? They are one of the two main classes of galaxies. Okay, our own Milky Way is a spiral galaxy. This is a very exciting view from Chile. Chile is a leading country in worldwide astronomy. Why? Because Chile में बड़े शहर बहुत कम हैं. Much of it is desert, and there is very little disturbance due to external light. So, कई observatories हैं Chile में, and this is one of these observatories. It is looking at the darkest, I mean not darkest, densest part of the Milky Way. No, but we are inside the Milky Way, so we can't really see the spiral structure. To see a spiral galaxy properly, we should go outside. And of course, we are outside all other galaxies. So we can see that, and see it from outside, this is the kind of thing that we see. Spiral galaxies are flat, चपटे होते हैं, रोटी की तरह. Most stars are close to the central plane, so the stars don't lie much outside the central plane. There's a bulge in the center, so it's more like a little stuffed paratha with a little in the middle, or like a dosa with the aloo in the middle. So there's a bulge in the center, which you can see clearly here. There's a little bulge. The best example, most studied because it is so close to us, is the Andromeda galaxy, or M31. So some smartphone maker has made a smartphone called Galaxy M31. Chance की बात है, or maybe it's deliberate, I don't know. So M31 is a name because it was listed by some person called Messier, who made a list of objects, and Messier की list में 31st object was what we now call the Andromeda Galaxy, M31. So, uh, Andromeda Galaxy is studied in such great detail because it's close enough so that we can see lots of detail. So now we come to the crucial argument and the only place in this talk where we'll use some mathematics. No, there are two places. This is one of them. So what's happening? So you have this central bulge. The stars are going around in a plane. Basically, the whole structure of the galaxy is planar. So it's like the solar system, but on a much bigger scale. Bigger meaning tens of thousands of light years, up to hundreds of thousands of light years. That's the kind of size we're looking at now. So the mass is in the center, just as the mass of the solar system is mostly in the sun, and the stars are orbiting this central mass. Then Newton's law of gravitation tells us how the velocity of the star will depend on the distance from the center. So I didn't want to keep the mathematics on the slide, but how many of you think that you can derive this? You हो जाएगा derive? V is equal to constant by root r. कैसे derive करेंगे? कैसे? अभी नहीं पढ़ा? न्यूटन लॉ पढ़ा है? सेंट्रीपिटल फोर्सेस पढ़े? तो कैसे नहीं होगा? So you put the gravitational force equal to the centripetal force. Okay. This constant is whatever it is. It doesn't matter. The main thing is that V is proportional to 1 by root r. So as r increases, V should decrease. And we see this in the solar system. Mercury goes around the sun pretty fast at almost 48 km per second. Whereas the outermost planet Neptune goes down slowly at 5 something km per second. That's also very fast. 5 km per second ना सो भी नहीं है, पर इससे तो बहुत कम है ना. In comparison, it's much less. And it follows. You can check out that the planetary speeds follow this 1 by root r very nicely. So this model works for the solar system. We expect it to work therefore for spiral galaxies also because the mass is similarly distributed. और यही पे पंगा है. It doesn't work. Now this will be a dark talk. Okay. So it doesn't work. We see something quite different. What do we see? As we move out towards the edge, so R, we go to higher and higher values of R. Instead of the orbital speed of the star decreasing, it remains constant. Okay, that's what we observe. So all the spiral galaxies which are close enough to measure the individual speeds of stars. अगर गैलेक्सी बहुत दूर है तो इंडिविजुअल स्टार्स को हम देख नहीं पाते हैं, रिजॉल्व नहीं कर पाते हैं. पर गैलेक्सी पास है जैसे एंड्रोमेडा एंड मेनी अदर नियरबाय गैलेक्सीज which have the spiral structure, we can do this calculation and check out that instead of falling off as 1 by root r, the speed is remaining constant. So what's going on? There are two possible explanations. Because we use very little, ना हमने कोई advanced physics use नहीं किया था. We use only centripetal force and Newton's law. Also use ही नहीं किया था. So there are two possibilities. Either Newton's law doesn't hold. That means Newton's law of gravitation is wrong. This is one possibility. This is a very extreme possibility. People won't easily want to go that way. So, or there is a second possibility. Or the mass distribution is different. It's different from what we are seeing. If the mass had been actually distributed in the same way, that is, all the mass of the galaxy lies in the plane and most of it lies in the central bulge, then it should follow that law 1 by root r. It doesn't. So that means there's more mass in the galaxy and it's distributed more evenly, not in the plane alone. ऊपर नीचे मतलब ऊपर नीचे क्या है? Everything is ऊपर. But जो भी है, the one side of the plane and the other side of the plane, both are equally populated with some matter, and this matter exerts a gravitational force, and that's why the speed doesn't fall. Now this matter is therefore dark matter because it's not the stars. From now on, in all the future slides, DM will stand for dark matter. Okay? DM is dark matter, by the way, don't forget. DM means many other things in many other contexts. In this it will mean only dark matter. So, the galaxy is full of dark matter. What is the shape? So, people can guess from various other measurements on galaxies which are nearby, like Andromeda, that it's almost equally distributed everywhere. That it's a spherical kind of shape, and it's usually referred to as a halo. So it's a spherical halo. Okay. Since this is a slightly tricky argument, I pause here. कोई doubt हो तो बताओ पीछे. I mean, if there is some need to repeat the argument, please tell me. Is the argument clear? What is the argument? 1. Using only Newton's law of gravitation and the formula for centripetal force, we can show that if the stars are actually lying in a plane, the velocity should fall off. 2. The velocity doesn't fall off. 3. Therefore, the stars don't lie in the matter, not star. The matter doesn't lie in a plane. The stars do, but the matter doesn't. The matter is distributed evenly. But this matter is not stars, so it is something else. It does not emit light. We don't see it in the telescope images. We guess its existence because of its gravitational effect only. So, this is dark matter. Now, as I said earlier, spiral galaxies are one of the main types of galaxies. There are two main types, plus there are many other shapes of galaxies. So the two main types are usually called, the second main type is usually called elliptical galaxies. And the rest are, there are many other types of galaxies. We don't have to go into that because most galaxies are either spiral or elliptical. So elliptical galaxies have also been measured in the same way. The argument tends to be a little more complicated because spiral is about simple and flat and you can use the solar system argument. But the conclusion is the same. Most galaxies are full of dark matter. Full means how much? There are many estimates, but estimates go from 80% to 90%, 95% rather, of the total mass. That means, जो में दिख रहा है, वो 10% है, 90% is invisible matter or dark matter. So this is galaxies. Now, before we go into other kinds of other places where dark matter is found, we ask this question. Remember, in the beginning we listed a question. What is it made of? चीज़ क्या है? So, मतलब ये किस तरह का पदार्थ है? So, what's the precise nature of DM in these galaxies? It's actually still an open question. It's the subject of current interest, research interest. So, one possibility is that they are planet-like objects, okay, or stars which have not yet formed fully. The star, before it forms, while it is forming, does not begin to emit light. So, a star that is still forming will be dark until at some point in its history it starts emitting light. So, ये भी possible है. Black holes are another possibility. By definition, black holes don't emit light. So there's a good name for them. These are called massive astrophysical compact halo objects, or machos. Does the word macho mean anything to you? Yeah? it does बोल दो यार क्या नहीं okay. So a common feature of these is that they are made of ordinary matter. Ordinary matter is also called baryonic matter. Does anyone know what a baryon is? Baryon क्या होता है? It's a kind of particle. What kind of particle? Can you give one example of a baryon which you know about? Not beyond your course. The name baryon may be beyond your course, but you know the particle. Two दे दो, एक नहीं है. This is big hint. दो particles तुम्हें पता है जो baryons हैं.
Electron and proton.
Proton and neutron, not electron. Electrons are different. So most of the mass is contained in protons and neutrons. Ordinary matter has its mass in protons and neutrons. So that's why ordinary matter is called baryonic matter. Okay. Baryons are particles that interact strongly. The electron does not interact strongly. So that's why it's not. But luckily, anyway, it doesn't count in the count of mass because it's so light that it doesn't matter. Matter यहाँ भी आ गया. So there's no room for machos, it seems. Why? Because if they're made of baryonic matter, they should reflect the starlight in this case, not sunlight, but starlight falling on them. Just as Neptune reflected sunlight, these objects in the halos of other galaxies will reflect the starlight. So even in our own galaxy, there should be lots of machos and they should show up in telescopes. Nazar aana chahiye na? They should reflect some light. Now there have been many searches which are specifically looking for this reflected light. And they don't find anything, they can only limit that it is less than this. So the conclusion is that even if machos do exist, their existence is not ruled out. But even if they do exist, they contribute very little mass to our galaxy, similar galaxies, and galaxies in general. So these baryonic or ordinary matter objects don't contribute much mass to the galaxy. That's the upshot. I think it's very appropriate. माचो का opposite क्या होता है फिल्मों में? In a Hollywood film, what's the opposite of a macho? बहुत शर्मा रहे हो तुम लोग. It's a wimp, ना? So, what's a? We have concluded this that unlike the dark matter in the solar system, which is made of ordinary matter, the dark matter and the halos of galaxies is something else. It's not ordinary matter. So, a favored category of candidate, it's not a single candidate, it's a type of candidate, is a weakly interacting massive particle. What does weakly interacting mean? You all know that there are 4 basic interactions, right? No, just stop. What are the 4 basic interactions?
हाँ बच्चों ये तो चैप्टर शुरू होते ही है फिजिक्स के.
बोलो. हाँ. Very good. Thank you. Thank you. So, strong nuclear force की तो बात हो रही थी. Baryons interact strongly. Protons and neutrons bind into nuclei and make up the mass of ordinary matter. But supposing there were particles that interact only by the weak nuclear force, apart from gravitation, of course, every particle interacts through gravitation, but weakly interacting, but very massive, say 1,000 times as heavy as the proton. This is a hypothetical particle. So that is what is called a WIMP. WIMP, weakly interacting massive particle. There is a problem with WIMPs. And the problem has to do with something quite different from these galaxies and the sizes and so on. What is that? There's a standard model of particle physics. The standard model of particle physics got established during the night, starting in the late 1960s with the work of Salam and Weinberg. And then the work of many others which contributed to it in the early 70s. It got established in the early 70s. And in 1983, it was experimentally confirmed by the direct observation of W bosons and then Z bosons. So, this showed that the standard model of particle physics must be essentially right. But this standard model has a problem. There is no such weakly interacting massive particle in it. उसमें कोई scope ही नहीं है डाले, वो तो particles are well defined. Okay, so you know what particles exist. You know, apart from the normal particles, there are these W and Z bosons, Higgs, etc. ये सब हैं. पर weakly interacting massive particle है ही नहीं उसमें. तो अब क्या करें? So what does it tell us? It tells us that supposing the galaxies, galactic halos contain a lot of weakly interacting particles, which are very massive, very heavy weakly interacting particles, their particle physics has to go beyond SM, beyond the standard model. It's worthwhile pausing here a little bit. सोच लो क्या, तो हमने देखा क्या और conclusion क्या है? हमने देखा कि galactic halos are not obeying what we expect them to obey. Okay. We are talking of hundreds of thousands of light years. Like our Milky Way's halo is typically 100,000 light years. And actually, new estimates go more towards 1 million light years. So you're talking about something that's 1 million light years and big sized objects. And we find some problem, something is not matching. And it's telling us that we should rethink the fundamental laws of physics at the scale of 1 FM. FM क्या होता है? Distance unit. What distance unit is 1 FM? 10 to the minus, excellent. 10 to the minus 15 meters, 1 Fermi or 1 femtometer. Both the short forms agree and have the FM as the symbol. So, particle physics, modern particle physics deals with distance scales smaller than 1 FM. 10 to the minus 15 meters की बात हो रही है, और वहाँ बात हो रही है lakhs of light years की. So this is something strange in a way and unique. I'll come back to this topic towards the end, this big and small argument. So I want to quickly move on because there's one more thing to cover, and before you get hungry, I want to cover that. And that is galaxy clusters. As we just discussed, galaxies are very big, but they are not the biggest structures in the universe. Most galaxies, there are some isolated galaxies, but most typically tens of which are solved. That kind of number, or maybe 1,000 galaxies. Together by their mutual gravitational attraction. When I say structure, a structure I am defining as something that holds together by its gravitational attraction. So just as a galaxy is held together by the gravity of the thing, so the clusters are also held together. So naturally galaxies are big, clusters are even bigger. Their typical size is 10 to 20 million light years. For example, the Coma cluster. Here's a picture of the Coma cluster. By the way, एक this piece of advice, नसीहत, ऐसे लोगों की आदत होती है ना कि नसीहत तुम्हें चाहिए या नहीं चाहिए. So you note that I am always giving the source of the image colon Wikipedia, the source of the image. If you ever show any images in your presentation, please cite the source. Okay, it is ethical to cite sources of images always. So this is an interesting image. It seems that this is a star, but in fact this is not a star. It's a galaxy, which probably contains a billion or 10 billion stars. Okay, so each of these star-like objects here is a galaxy. Okay. This is the coma cluster, and this is what our modern telescopy is able to show us. It's amazing. Huh? It's a mind-boggling thing that you're able to see such a huge thing like this. Now what do we expect? This is the second slide where there is some maths. Second and last slide where there is some maths. When a system of gravitating objects has been around for long enough का क्या मतलब है? No, a physics way of saying it is when it has reached equilibrium. That's what long enough means. If it has reached an equilibrium, then we expect the average energy of motion of each of the members to be proportional to the energy of interaction. In fact, you can prove a more quantitative result, which I am only mentioning here, because this one can't be proved with your present knowledge. The previous result could be proved. 1 by root r can be proved with what you have studied already. This one needs a little more, but at BSc level, I am sure you will go through a proof of this. This result is called the virial theorem. And the virial theorem has many forms, but the virial theorem for gravitating system says this, that the average kinetic energy is half of the absolute value of the average potential energy. Same order के हैं, but actually exact proportionality is not half. But it doesn't work. Again, this is another case of mismatch, where our expectation is not working out. Galaxies in most clusters seem to move faster. That is, the average kinetic energy seems to be much higher than expected from the knowledge of the potential energy. So that suggests that the potential energy sources have not all been counted. That there are more sources of gravitational attraction which we are missing, and sources of gravitational attraction which we miss because they are invisible. They are not emitting light. So the conclusion is the same. That there is dark matter in the clusters. I want to mention this gentleman because most people have, we hear names of Einstein, Chandrasekhar, etc. We don't hear the name of Zwicky. Zwicky was a Swiss astronomer who actually first used the phrase dark matter. Dark matter शब्दों का इस्तेमाल सबसे पहले ज़्विकी ने किया था और लगभग 100 साल हो गए हैं. Back in 1933, and it is instead studying the coma cluster which we saw just now. We saw a modern image of the coma cluster. Zwicky had access to an old images, and Zwicky estimated that the cluster mass was 400 times the mass of the stars. So, in other words, he thought there was a huge amount of dark matter. The modern estimate is not so much, but it's still pretty much the cluster is dominated by dark matter in terms of its total mass. Modern estimates would say somewhere around 90%. These are rough figures. Astronomy में इतने precise figures आते नहीं हैं. It's an estimate. So roughly 90% is a good enough figure. Roughly 90% of the total mass of clusters is things that are not visible, and therefore dark by definition. Now I will go a little more quickly through these two slides. This is the role of dark matter in cosmology. I mean, this, I'm going quickly, but this is what makes it interesting. So, we find that dark matter is widespread in the universe and it exists at different distance scales. So, it likes to play an important role in the structure in the universe. So, most cosmologists believe that in the history of the universe is something that is interesting from a cosmological point of view. Okay. पहले क्या था, अब क्या है? Then in the history of the universe, dark matter played a crucial role. So there are different kinds of evidences. For example, some Hindi poet has called Brahman. Is the microwave background radiation, which is all around us. That shows tiny wiggles. Initially it was thought to be totally isotropic, but now we see the tiny wiggles. Those tiny wiggles tell us something about the history. हुआ क्या था पहले? And the formation of galaxies and the formation of clusters all together tell us about 85% by mass of the total matter in the universe will be dark, if not more. So now we are coming to recent results. Recent meaning last 10 years. So the Planck satellite was a satellite which was meant to probe the microwave background radiation plus many other things. It was sent up in 2009. देखो हम लोग 21 सदी में पैदा हुए ना, हमारी आदत है 90 से शुरू करना, but your years should start from 20, not 90. So 2009 the Planck satellite was set up. It stopped collecting its data in 2013, but the data were published in many installments later. So this is from the Planck 2018 data. I believe that is the last one. Many newspaper articles, internet sites, etc. will give you slightly different numbers for these. Doesn't matter. The basic idea you should get. It tells us that the energy of the universe is contributed only to the extent of only 5% or so by ordinary matter, baryonic matter, 4.9% according to this estimate. Dark matter makes up more than 5 times of that. 26.8% is dark matter. And 68.3% is made up by something called dark energy, which is beyond our scope in this talk. उसकी हम बात नहीं करेंगे unless somebody has a question about it. So, I'll come to the concluding slides. Two concluding slides. One is that there's lots of dark matter in the universe. We ourselves are part of the dark matter story. Then there's baryonic dark matter and there's other kind of dark matter. The word we don't know what exactly. इतना कह सकते हैं पर exactly क्या है नहीं पता. A general word used is exotic. Exotic है मतलब कुछ अजीब है. So exotic matter, but more precise is just to say non-baryonic. It's a subject of current study. Now I return to my large and small point as the final closing slide. Actually, there's one slide after this, but this is the closing slide. Dark matter connects our understanding of very large things. I'm repeating now. This is a repetition. Cosmology, we are talking about millions of light years, and very small things. We are talking about less than 1 femtometer. This is something no one would have imagined 100 years back. Einstein didn't know this, that there would be such a connection. So, we are lucky, and you people are even luckier, because you will, if you stay on in science and decide to become वैज्ञानिक, अगर वैज्ञानिक बनते हैं आप लोग, which is an option you have, you can decide to become a scientist, but some other kind of scientist also, not necessarily someone who's studying physics and cosmology in particular. But if you do study this field, you are living in an exciting time, because who are you? What are you trained in? I am trained in particle physics, high energy physics. What do I do these days? I do cosmology. Why? Because the two are connected. And that's something that no one could have imagined. So at the end of my career, I am seeing this connection very closely. At the beginning of your careers, you'll be able to see this and take it further forward. So I think that this is an exciting field of study, and this is an exciting time to be starting the study. Say 5 years from now, some of you may be starting research in this field, and you are really lucky. My last slide. Okay. So I'll stop here. I can take some questions if the organizers allow, and the other members of the audience. अगर लोगों को भूख इतनी ज़्यादा नहीं लग रही है, अगर अभी भी थके नहीं हैं और सवाल पूछने को तैयार है,
We are young, sir. Bear the pain of
भूख तो इतनी ज़्यादा लगती है ना हमारी।
I'd like to thank you, Mukherjee sir, for such a wonderful lecture in cosmology and enlightening our students. Hope they like it. Yes? Thank you so much, sir. It's a pleasure to have you in our campus. Now I would like to call Dr. Gaurav Sharma just for a small note. He's going to tell about the practical, when it's going to happen.
बच्चों आवाज आ रही है मेरी? वॉइस आ रही है? चलिए, आपने 2 लेक्चर अटेंड करे। आज थोड़ा लेट हुआ प्रोग्राम, लेकिन कल से ऑन टाइम होगा और प्रोबेबली 9:30 वी विल स्टार्ट ब्रेकफास्ट करके, ठीक है? इससे ये लेक्चर लेते हुए भूख ना लगे। और अब आपको लंच करने जाना है, ठीक है? और दूसरी बात, लंच के बाद आप अपना लंच लीजिए। देयर आर लैब्स, थोड़ी देर की लैब्स हैं आपकी, आप लैब में जाएंगे। मैं आपको स्कूलों के नाम बता रहा हूँ, किसको किस लैब में जाना है। लंच करना 15-20 मिनट बाद, करीब 2:10 से आप लैब में पहुँच जाइए। 2:10, हाफ एन आवर इज इनफ टू टेक लंच। उसके बाद आप लैब में जाइए। आज आपकी फिजिक्स की, कंप्यूटर की और केमिस्ट्री की लैब कराते हैं। रोज आपकी चेंज होगी, ठीक है? और मैं आपको रूम नंबर बता रहा हूँ, थोड़ा सा नोट कर लीजिए बेटा। एक नोट कर लीजिए जिसे जहाँ जाना है।